Next topic, construction. The important parts of alternators are stator and rotor. So let's first discuss about stator and then we go for rotor. Stator. Stator is a fixed part which is used to house the armature winding in the slots present in the stator, and here in stator slots are present in inner periphery and which is used to house the armature winding, means conductors. And now let's have a close look on the stator slot. Let us suppose this is the stator slot and this be the conductor placed in the slot, okay, and there will be insulation present between the stator slot and the conductor, and there will be one wedge made up of silicon steel, and this wedge is used for making the conductor not to slip from its position. And here open type of slots are employed, and there are three types of slots, that is fully open slot, semi open slot and fully closed slot. So here fully open type of slot is used, and stator is made up of cold rolled non-direction oriented steel with 3% of silicon. So stator is made up of cold rolled non-direction oriented steel. Here non-direction oriented is used, whereas direction oriented is suitable for linear structures. This is not a linear structure, so non-direction oriented steel is used, and 3% of silicon is added. 3% of silicon is added to reduce the eddy current losses, and stator is laminated. Here lamination means instead of taking a solid piece, this solid piece is built up of thin sheets of laminations, and in between these thin sheets of laminations there will be an insulation present, and now all these thin sheets are joined together and which makes up to look like a solid piece, and this is the laminated structure. So stator is laminated. Why? Because to reduce the eddy current losses. If the structure is laminated, resistivity will increase so that the eddy current losses will get decreased. So here in stator, to reduce the eddy currents, in the material 3% of silicon is added and structure is laminated, and this insulation could be mica or other depending upon the ratings. Next, there are two types of rotors, that is salient pole type rotor and second cylindrical pole type rotor. Alternator which employs salient pole type rotor is called as salient pole alternator. Whereas the alternator employing cylindrical pole type of rotor is called cylindrical pole alternator. Now let's discuss about the salient pole type of rotor. the name Salient means poles are projected outwards. This is the front view of the salient pole type of rotor, and these are the poles. And to form these poles, rotor requires DC excitation, and to act this pole as north pole, wound the winding like this, and to make this act as south pole, wound the winding like this, and start like this. So now, by this way of connection, here this pole acts as north pole, this pole acts as south pole, this pole as north pole, and this pole as south pole. So with this type of rotor construction, the flux distribution in the air gap will be non-sinusoidal. Which is not desirable, because alternator is expected to generate pure sinusoidal induced EMF. For that, it requires pure sinusoidal flux distribution in the air gap. Whereas with this pole type of rotor, the flux distribution is non-sinusoidal. So with this non-sinusoidal flux distribution, we get non-sinusoidal induced EMF, which is not desirable. So we have to make this flux distribution sinusoidal. For that, a little modification is done in this construction, that is using chamfered poles. With this chamfered poles, the salient pole type of rotor looks like this. So now let's analyze how this chamfered poles of rotor construction makes the flux distribution in the air gap sinusoidal. For that, consider this chamfered pole and the stator like this, and let the conductor of consideration be here. Let us suppose that rotor is rotating in clockwise direction, and as this rotor moves towards the conductor, observe the air gap between the pole, sheave and conductor. So here, as the pole tip approaches the conductor, air gap reduces. As air gap decreases, flux will increase, means like this. And upon reaching the tip here, then the flux will be maximum. And next, when the pole tip crosses the conductor, then observe the air gap will increase. So as air gap increases, flux will decrease like this. So this is how, with this type of construction, the flux distribution in the air gap can be made sinusoidal. And whereas here, with this type of construction, the flux distribution is non-sinusoidal, because at center of the poles, flux density will be maximum. So there is a chance of saturation. Because of that saturation, here the flux distribution will be non-sinusoidal. And to make the flux distribution sinusoidal, we are going for chamfered pole types of salient pole rotor construction, whereas this is called as normal salient pole. So with chamfered poles of rotor construction, we got sinusoidal flux distribution, and with sinusoidal flux distribution, our induced EMF will become sinusoidal. And here the other important topic to be discussed is damper windings. Also called amortisseur windings. So first let's discuss about the functions of damper windings, and then we can go for what does damper windings mean and how they are employed. Functions. Mainly in synchronous machines, damper windings are provided to eliminate or reduce hunting effect. So what does hunting effect mean? So hunting effect is the momentary oscillations produced in the rotor because of the disturbances. That disturbances could be from the load side or from the input side, that is from the mechanical power input side or from the excitation side. Actually, alternator is intended to rotate at synchronous speed, but because of that disturbances, so rotor will tend to move to and fro. That to and fro motion is not desirable. So there is a need to reduce that to and fro motions. So that to and fro motions means that momentary oscillations produced in alternators because of disturbances is called hunting effect. And in case of alternators, negative sequence currents during short circuits. So if there is any short circuit, then there is a chance of negative sequence currents inducing in the rotor. Because of that negative sequence currents inducing in rotor gets heated up and obviously it gets damaged. So in order to avoid that, damper windings are provided. So damper windings provides the path for those negative sequence currents and reduce those negative sequence currents so that rotor will not get heated up. And in case of synchronous motors, damper windings are provided to provide starting torque. We know that synchronous motors are not self-starting, so there is a necessity to provide starting torque, which can be provided by using damper windings. So with damper windings, initially synchronous motors rotate like induction motors. So upon reaching close to the synchronous speed, now because of magnetic locking, the motor achieves the synchronous speed and will continue to rotate with synchronous speed. Damper windings are the copper bars inserted in the slots of pole shoes. Means if this is the salient pole rotor, and these are the slots present in the pole shoe of salient pole, and in these slots copper bars are inserted and their end connections are short circuited by copper rings on both sides. So damper windings are the copper bars which are inserted in the slots of pole shoes and short circuited by the copper rings on both sides. So if you forgot about this salient pole rotor, now let's see how the damper winding looks like. So these are the copper rings, and these are the copper bars. This structure looks like a squirrel case rotor. Okay, so from this you can note that there will be induction motor or induction generator action taking place because of damper windings in the alternators. So now let's see how the damper winding reduces the hunting effect. For speeds less than synchronous speed, because of damper windings, induction motor torque produces and accelerates rotor to synchronous speed, and upon reaching the synchronous speed, then the induced EMF in the damper winding will be 0, so that now machine will run as it is in normal conditions. And for speed greater than synchronous speed, induction generator torque produces and decelerates rotor to synchronous speed, and upon reaching the synchronous speed, the induced EMF in the damper winding will be 0, so that the machine will run as it is in normal operating conditions. So from this you can observe that, as you know that alternators must run at synchronous speed, but because of the disturbances, what is happening means to and fro motions, to and fro oscillations are happening in the rotor. Means rotor is trying to rotate more than synchronous speed and trying to rotate less than synchronous speed. So these to and fro motions must be reduced, okay, which can be reduced by employing damper windings in the salient pole type rotor. So because of damper windings, these to and fro motions of rotors about synchronous speed is reduced, means hunting effect is reduced. Next, salient pole type rotor is laminated structure. Laminated in order to reduce the eddy current loss. And if you observe the salient pole type rotor structure, this is mechanically unbalanced. Means if you use this rotor for higher speeds, because of centrifugal forces, okay, this structure can't withstand. So is why this type of rotor structure is employed for low speeds. Low speeds means that is up to 1000 rpm. As this is employed for low speeds, so this rotor employed alternators are used in hydro power plants. And this salient pole type of alternator is also called as diesel engine driven alternators. For fixed power and voltage, P is directly proportional to D square L, where D is diameter and L is length. So L by D ratio must be 0.2. From the design consideration point of view, L by D ratio must be 0.2, which means for lower speeds, D must be high and L must be low. Next, cylindrical pole type rotor. So this is how cylindrical pole type of rotor looks like, and here 2/3 of rotor periphery is slotted and 1/3 is unslotted for pole formation. Means this is the 1/3 rotor periphery which is left unslotted for poles formation, and these are the rotor slots for placing the conductors. So in order to form the poles, rotor requires field excitation. So let us suppose this is the DC voltage which is needed for the excitation. In order to make this portion act as north pole, make the current flow in the conductors like this. Means current must be tending towards outward side, and then like this, and then like this, and this connected to this, like this, and this is connected to the two terminal of the field excitation supply. By connecting the winding like this, you can make this portion act as north pole and this portion act as south pole. And the other point to be noted here is cylindrical rotor is not laminated, and here it is made up of solid steel with chromium or molybdenum added to increase the mechanical strength. So if you observe the rotor structure, this is mechanically balanced. So as this is mechanically balanced, this can be employed for higher speeds. So from design consideration point of view, okay, D must be low and L must be high, which implies as P is directly proportional to D square L, that implies L by D ratio must be 5. Here this cylindrical pole type of rotor is not laminated. Why? Because this solid cylindrical pole type rotor itself acts as a conductor, and whatever the eddy currents produced in this solid structure will produce the required dampings to reduce the hunting effects, so that this structure need not be laminated. And as this is employed for higher speeds, it is used in thermal power plants. And the other concept to be discussed here is what we have seen with normal salient pole type of rotor is the flux distribution in the air gap is non-sinusoidal. So because of this non-sinusoidal flux distribution, we are getting the non-sinusoidal induced EMF. And to make this flux distribution sinusoidal, we are going for chamfered pole type of rotor construction. With this, we got sinusoidal flux distribution, so that output from the salient pole type of alternator will be sinusoidal. So if you observe the cylindrical pole type of rotor, okay, there will be uniform air gap present between the rotor and the stator throughout the periphery. So the flux distribution because of the cylindrical rotor will be like this, which is highly not desirable. So how to make this non-sinusoidal flux distribution to sinusoidal means by using distributed winding. So now let's see how this distributed winding makes our flux distribution sinusoidal. Okay, for that consider a slot like this, and let us suppose the three conductors of the same phase are placed in the same slot, means concentrated winding. So now let's see the EMFs induced in the 3 conductors placed in the same slot. Okay, let this be the EMF induced in the first conductor, and let this be the EMF induced in the second conductor, which is placed in the same slot, and let this be the EMF induced in the third conductor, which is placed in the same slot. And now the resultant of 3 conductors EMF will be this one, so which is non-sinusoidal. And now let's see how the EMF will be sinusoidal with distributed winding. Means, so I am placing the 3 conductors of the R phase in different slots, means winding is distributed. So with that, EMFs induced in the each conductor of same phase which are placed in different slots will have some phase difference, and let this be the EMF induced in the conductor placed in this slot, and let this be the EMF induced in this slot conductor, and let this be the EMF induced in the conductor. Okay, and on whole together they will add up, and the resultant will be like this. So from this you can conclude that with a distributed winding, the induced EMF will become sinusoidal. So in cylindrical pole type of rotor, windings are distributed to the maximum extent. As cylindrical rotor is mechanically balanced, so it can be used for higher speed. So used for up to 3000 to 3600 RPM. And now let's discuss some of the important concepts which we have to discuss for understanding the upcoming topics. So first, why frequency of generation is 50 Hz or 60 Hz. Steam turbines gives good efficiency at 3000 to 3600 RPM. Okay, and we know that diameter D is directly proportional to the number of poles, and from the design consideration point of view, for higher speeds diameter must be low. So as diameter is low, number of poles will be low. Low number of possible poles are n is equal to 2, and as we know that speed n is equal to 120 F by P. So with P is equal to 2 and n is equal to 3000 RPM, frequency we get is 50 Hz, and with P is equal to 2 and n is equal to 3600 RPM, F is equal to 60 Hz. So this is why the frequency of generation in some countries is 50 Hz and in some countries 60 Hz. How energy is generated by alternators? Okay, let us consider this as cylindrical rotor, and let us suppose this as the stator, and this rotor is free to rotate and which is supported by keying the rotor slot with shaft. And in power plants, alternator input is given by prime mover, which is usually steam turbines, and to the same shaft a DC generator, which is self-excited DC generator. Our cylindrical rotor alternator, and the DC output from this is given to the rotor through slip rings. So now let's analyze how energy is generated by alternators in power plants. So with the help of this steam jet, the turbine blades in the prime mover will rotate at the speed governed by the speed governor, and as the shaft is connected to the rotor, so rotor also rotates at the speed maintained by the speed governor. But here there will be no rotating magnetic field created because poles are not created. For poles to be created, here DC excitation is required, and so that onto the same shaft a DC generator is mounted, and now as the prime mover rotates, this DC generator rotor also rotates, and because of this self-excited DC generator, EMF will be induced, which is converted into DC by the split rings, so that DC output voltage is available at these terminals, and this DC output voltage is given to the rotor of alternator through slip rings, so that now poles are created in the rotor of cylindrical alternator. And now as the poles are created and the rotor is rotating at the speed maintained by the speed governor, now the rotating magnetic field will be created in the air gap between the rotor and stator, and as this rotating magnetic field cuts the conductors which are placed in the stator slots, okay, EMF will be induced in that conductors, and that induced EMF is collected from the output terminals. Okay, and usually the output terminals will be R by B, means the phase sequence followed will be R by B, and these three windings are connected in star. Okay, and why it is star and why it not in delta will be discussed later. And next, to find direction of EMF induced in conductors of alternator. Okay, as you know that in case of DC machine construction, simply conductor will be on the moving part, rotor. So as the rotor rotates, the direction of motion on the conductor will be downwards. Okay, and the field direction will be from north to south. So by applying Fleming's right hand rule, we can find the direction of induced EMF in the conductor. How means to apply Fleming's right hand rule, it is needed that the magnetic field direction and motion direction must be known, so that the induced EMF direction can be known. So place your index finger along the field and thumb along the motion, so that by applying Fleming's right hand rule, you can find the direction of induced EMF by the direction of your middle finger. But whereas in case of alternators, conductor is on static part. Okay, let us take the salient pole type of alternator, and to find the direction of induced EMF in this conductor, okay, we need the direction of motion and field direction. Field direction obviously you know that from north pole, but as the conductor is on static part, how can we determine the motion of this conductor? So here is the answer, and here the rotor direction is taken as reference. So if rotor is rotating clockwise, then conductor will appear to rotate anti-clockwise. Okay, so take the motion direction opposite to the rotor direction. So this is the convention which we will use in further discussions, so please remember that. Okay, now you know that field direction and motion direction, and now by applying Fleming's right hand rule, simply find the direction of induced EMF. Next, pole formation. On stator of alternator. Consider this salient pole type of alternator, and let us suppose this be south pole, this be north pole, and this be south pole, this be north pole, and let these be conductors. here, and let this be rotor rotating in clockwise. So by applying Fleming's right hand rule, find the direction of induced EMF here. So by applying Fleming's right hand rule, okay, we need the motion direction. So as we from the previous discussion, we have decided that to take the direction of motion of conductor opposite to the direction of rotor. So motion direction like this, field direction like this. So by applying Fleming's right hand rule, you can find the direction of induced EMF, so which is outwards. Okay, and so obviously this will be cos, this will be dot, and this will be cos. Okay, and now to find the poles formation on the stator, simply remember the corkscrew rule. What it says, so the direction of the rotation of head will represent the direction of flux, and the advancement of tip will represent the direction of current. So if the direction of rotation of head is anti-clockwise, then the direction of advancement of tip is outwards. Means if the flux direction is anti-clockwise, then the current will be outwards. If the flux direction is clockwise, then the advancement tip will be down, means current direction will be down. So here the direction of current we took is outwards. So the flux direction is anti-clockwise, and here clockwise. So if you observe here, the fields add up, and here the fields get divided, and here the fields get added, and here the field gets divided. Means this portion acts as north pole, and this portion acts as south pole, and this portion acts as north pole, and this portion acts as south pole. Okay, as the EMFs are adding, we know that the field direction is from north pole to south pole. So as field is coming from this portion acts as north pole, and this portion acts as south pole. So this is how the poles are formed on the stator periphery of the alternators.